It's very easy to see what kind of compound inequality I have whenever that word and is chilling right between my two pieces. That lets me know what my final graph should probably look like with two dots and shaded between. So I'm going to go ahead and solve each of these sides independently, drop the word and down to form a barrier between the two, and see what I get. On the left-hand side, I'm distributing that 2, so I get 2x plus 2 greater than or equal to 4. And as I continue on with the problem, I'm going to subtract 2 from both sides. I get 2x on the left. It's a positive 2, which is good because I'm not going to have to flip the sign. And then I get a positive 2 on the right. So in my last step, I divide by 2. I end up getting x on the left, who's now isolated, is greater than or equal to 1. So all of my solutions have to be greater than or equal to 1. That's part of the stipulation. Now on the right-hand side, I solve this one also. Add 31 to both sides. I get 35 on the left is greater than or equal to 5x. That is a positive 5, so I do not have to switch the direction of the sign. In the end, I have 7 is greater than or equal to x. Or you could read it as x is less than or equal to 7. So my numbers were bigger than 1, and they have to be less than 7. Or it could be equal to either of those two values, 1 or 7. So those are the stipulations on the different values that make my compound inequality true. To make this more visual, we give ourselves a number line. I'm going to put 0 and 1 and 7 as my reference points, somewhat scaled. I know that I have two solid dots. And since we just discussed that the shading is between, because it's all the values bigger than 1, less than 7, or equal to either of those values, that right there is my final graph, which is a great visual way to look at the infinite number of solutions there are to my compound inequality. Now when I look at a second example, it might be a little bit more difficult to realize that this is an and compound inequality. If I were to rewrite this, the original problem might have looked like this: negative 13 less than or equal to 3x minus 1, and 3x minus 1 less than or equal to 20. As mathematicians, if we can get away with not writing things multiple times, we go ahead and do that. So if I look here in the middle, I really just condense this down, take away one of the values, and then I write my final answer as negative 13 less than or 3x minus 1 less than or equal to 20. And I take away that word and in the middle. So really, this is an and compound inequality that I'm dealing with. So if we go to solve this, I want to look at it in a very specific way. Sometimes it gets a little bit overwhelming. So for right now, just ignore the fact that the negative 13 part is there. And I ask myself, how would I solve this inequality? And the answer is I would add 1 and add 1. Now if I go back and bring this part back in, and instead ignore this half of my inequality, again I find myself adding 1 and adding 1. So when I take that away and look at the whole thing, it's possible for me to solve this whole compound inequality at one time. I'm solving more or less 3 sides to this inequality. So I end up with a negative 12 is less than or equal to 3x, because those ones canceled out. And then he is less than or equal to 21. Now I want to get this 3 by himself. He's attached with multiplication. So I'm going to divide everybody by 3. Those cancel out. I'm left with negative 4 is less than or equal to x is less than or equal to 7. Or my solution set being all the numbers between negative 4 and 7, including negative 4 and 7. So if I go to graph that on a number line, put 0, negative 4, and 7, I'm going to have 2 closed dots again, right there, and I'm shading in between. So that's a great visual way to look at all the solutions to my compound inequality. So if there is no word and, but I have one long string of inequalities, I'm going to treat it like an and inequality.